Hi, Mr. C, and anyone else who might be watching this. Welcome to AP Physics on Ice. There's no ice because the Queen of Diseases may have contracted one of her own, but plenty of physics, so let's get into it. So, why is physics important to skating? Ice rinks have featured in many a physics problem, and it's no surprise. A lack of friction makes ice opportune for calculations, but more importantly, skating is defined by motion. From lutzes and loops to dodging defenders to kids slamming into walls during free skate, physics is behind it all. The aforementioned examples involve kinematics, rotational motion, collisions, and lots of energy. Who would have guessed that sliding around on knife boots warranted this much analysis? Well, I did. That's why we're here. For example, until a few years ago, skaters would earn more points during jumps by having their arms above their head because it changed their center of mass and made them spin faster. Let's find out why. Alright, so just like I was talking about, our first scenario is spinning. Now, as you can see, we didn't quite make it to the rink, but the purpose of this scenario is to prove conservation of angular momentum, so when the moment of inertia is decreased as a person pulls their arms into their chest, the angular velocity will increase, and determining friction between the blades and the ice. I did an at-home version, but the concept is basically the same. Somebody's recorded spinning on skates or on the floor in socks with a video camera. They start with their arms out, they pull them in. Their mass should be measured or known, and the mass of their arms alone. I used weights, so I used the mass of the weights, and then like 5% of a human's body weight is the weight of their arms. So I just put that in kilograms. And the radius of the skater and the radius of blades, as well as adding the length of an arm to that radius. For the radius of blades, I did like the ball of my foot because that was the surface I was spinning on. But yeah, that's so that friction can be determined, which you'll see in the next slide. So here are our variables for scenario 1. We got our measured variables and our calculated variables. We got the mass of the skater, that's me, or spinner. We have the mass of the weights and my arms combined, radius of the person, it's an imprecise science, length of arms, length of the ball of the foot, all the stuff we discussed, and a couple of things that we got from the video, time and number of revolutions, as well as a bunch of variables that we'll calculate later, moment of inertia and angular velocity. And here we have our calculations for scenario 1. We're proving the conservation of angular momentum. First, we calculate our moment of inertia with the arms out. And so we have the basic cylinder 1/2 mr squared plus the moment of inertia with the arms and the weights combined. And I believe that's from the parallel axis theorem. And we have a lot of asterisks here, basically just adjusting for, do you have weights added to your body weight? Do you have arms and weights taken, like, do you have your arms taken away from body weight? So that's what all those are. And then you just put in your values. You get 1.78. And you have your second moment of inertia, where the arms are in with the body. Again, you're adding the weights here, so you plug in and you get 1.21. To find the first angular velocity with the arms out, you take the number of revolutions rather, with that being 3 over the amount of time, 3.85 seconds to get 0.78, and then same process with the second angular velocity, to get 0.87, and we're going to try and see if they're equal, right? Multiply the first rotational inertia times rotational velocity, the second rotational inertia times rotational velocity, and they are just a little bit off, which is due to experimental error. But you can see that they end up nearly the same amount, proving conservation of angular momentum. And now for the second part of scenario 1, where we slow down to a stop and calculate the force of friction. We have just basic kinematics equations in rotational form manipulated here. Change in rotational velocity is over time is equal to acceleration, and you've got that broken down further. Number of rotations over time squared to get 0.76. Newton's second law in rotational form, sigma torque equals I alpha, and we're using all of the measurements from the second period, of course. And here we get 0.92 for our sum of torques, and then you divide that by the radius, which is the ball of my foot, and you get 10.22 newtons. And now scenario 2, involving much more skating, albeit not the ice kind. We have my sister and I here in the lovely video with rollerblades. We are trying our best. And the methodology for this one, we are proving conservation of linear momentum and determining the peak force between the two skaters who are pushing off of each other. So you're going to film them, mark the ice where they begin and end, make sure you mark time too. We use chalk on the sidewalk. You can use a Sharpie on the ice, which I never knew that the skating instructors were using those, but I digress. And then you measure the distance traveled by each, measure the mass of each skater, or know the mass of the skaters, and the length of their arms so that you can find the peak force. As for our variables for scenario 2, once again, we have our measured variables, our calculated variables. We have the mass of each skater, we have the combined arm length, displacement of each of them, and the time it takes for them to stop, and we'll be calculating the larger skater's velocity and the smaller skater's velocity, notated, let's say, as big V and little v. We've got a lot of big and little here. First thing we're doing, once again, is conservation of momentum. This time is linear. mv plus mv equals 0. Should be pretty simple, except for the fact that we're not on ice. So it ends up being a little off. But you have big V is equal to the distance traveled by the largest skater over the time it takes for them to stop. And you get a displacement of negative 0.59 if the smaller skater is moving in the positive direction after they push off of each other. And then you have little v equals the displacement of the smaller skater over the amount of time it took for them to stop. You can see it's less time, it's foreshadowing here. And you get this velocity, 0.53. And then you add them together, multiplied by each of their respective masses, and it should be 0, but you get negative 10.25. And we figured that this was due to friction between the wheels of the skates and like their bearings, because Eva had a lot older skates than I did on, and so that's going to affect how quickly they slow down and, you know, how easy it is to start moving. Oh, being on ice obviously would make it a little bit easier because you only have one point of friction. Like, you're not slipping on the ground, you're just sliding on the ice, and there's no rotational element. Here's our second set of calculations for scenario 2, in which we determine peak force. So first you get the kinetic energy of each of the skaters, and it's just 1/2 mv squared broken down into displacement over time again. And we get 5.99 joules and 9.71 joules respectively. And then to get the average force, you do the total kinetic energy divided by the distance, or the combined length of the arms. And the reason why you use total kinetic energy is that energy is a scalar, not a vector, and so they're both positive values, and like the total energy of the system is both of them added together. And divided by, and so that's the amount of work that they do on each other to get moving from rest, and divide that by distance, you get force, and that is 9.51 newtons. And then just multiply average by 2 to get peak for 19.02 newtons at peak. Alright, and since the segment went so awry, I decided to calculate the energy dissipated and the friction that dissipated it. So we labeled our ideal velocity for the little one V ideal. Very clever. And so basically this is what would happen if conservation of momentum actually worked out. We've got big M, big V over little m, because they're equal. They should be equal. And so you can see the calculations here lead us to 0.77 meters per second. And so the dissipated energy would be 1/2 times little mass times ideal ideal velocity squared minus actual velocity squared. And that's basically just distributive property of 1/2 mv squared minus 1/2 mv squared. And then you get 6.71 joules. And again, you use the formula force equals work over distance. And over that distance of 2.64 meters, you get 2.54 newtons of force between the wheels and their bearings that prevented my calculations from being perfect. How tragic, but science. And now we have our final scenario, pushing another skater along the ice/concrete, the kind of stuff we do when we're fooling around pretending to ice dance. So it's pretty self-explanatory. One skater's pushing another until they let go, and then they slow down and stop. I'm sure the video is playing right here. Yeah, I'm heading in the right direction. Oh, look, I just did it. And then you determine coefficient of kinetic friction and applied force by filming the skaters pushing each other, and then you mark where they stop being in contact, and then where the second skater stops, and you measure the mass and displacement of the second skater so that you can find the amount of friction. Variables for scenario 3. Once again, we have our measured variables, our calculated variables. We have the mass of the skater pushed, we have the displacement while they're being pushed, and the displacement after they're released. Anything with subscript 1 is while they're being pushed, subscript 2 after release. The time that they're pushed, the time that they spend sliding or rolling, the acceleration, and then the calculated variables are acceleration while pushed and after released, and the velocity immediately after release, which functions as the initial velocity for the second period, final velocity for the first period. And then you start at 0 either way, or you start and end at 0 rather. And the time has come to calculate. For scenario 3, coefficient of kinetic friction. Our velocity at the end of the first period, beginning of the second period, I'm just going to call it velocity from now on out, will be calculated by 2 times the displacement of the first over the time of the first. And the reason that you're multiplying by 2 is because we're looking for the final velocity, not the average velocity. And so that comes out to 3.8. And then your acceleration during the second period as it slows down. This is just, again, a manipulated kinematics formula. It's, you can think of it as whatever is left over from initial velocity times time over time squared. That's all this is. And so you end up with negative 2.13. It should be negative because you're slowing down. And then to get the force of friction, it's equal to ma, Newton's second law again. And by multiplying the acceleration, absolute value of the acceleration, by the mass of the skater, you get 91.59 newtons of force. And the coefficient of kinetic friction is the force of friction divided by normal force, and since there's no other forces messing around with normal force, it's just equal to mg, and so that comes out to 0.213. And now, using the friction that we just calculated, we can determine the applied force during the first period and the work done by the skater pushing the other skater. And so to determine acceleration, you've got 2 times the first displacement over delta t squared, again derived from kinematics equations, and you get 0.79 meters per second squared. And the applied force is equal to mass times acceleration plus the force of friction, because the net force is the applied force minus the force of friction. And so there you have m times a plus friction equals 125.56 newtons. And that's the force I was pushing with. Pretty strong, eh? And the work that I did when I was pushing the child can be calculated by force times distance or displacement, delta x1, whatever you want to call it. Results the same, 1145.11 joules to get her up to that speed. And stop relatively quickly. Interesting how physics works. Now, finally, we've reached our conclusion, 2 drums and a cymbal. This experiment certainly proves one thing. In real life, nothing is ideal, such as filming this on my 4th take at 1 a.m. with a voice as hoarse as it's ever been. As much as we'd like to assume a frictionless surface or a spherical cow, there are endless confounding variables out there for which physics and engineers must account. With regards to my results, it can be concluded that variations in rollerblade bearing lubrication as well as human error in movement and measurement likely reduce precision. Nevertheless, the physical principles behind skating were clearly demonstrated, such as that nifty conservation of angular momentum. And additionally, it's been proven exactly why we use real ice in physics problems. Maybe I'll try that out over the summer, escaping the heat waves. Until then, this is Zoe Weiner signing off. Mr. C, please consider giving me 100. I worked very hard on this. Thank you.